Welcome to lesson 25, the definite integral. So in the last lesson, we learned that the limit as n approaches infinity of a Riemann sum could be used to define the area under a curve for a function over an interval. And just like in just like in limits, we had a limit that was a slope of a tangent line, and then we gave it a name, called it a derivative, and it turned out to have a lot of applications. The same thing is going to happen here. This limit as n approaches infinity of a Riemann sum is going to be given a name in this lesson, and then for most of Calc 2, you're going to be working with this thing that we're about to define. So we are going to start by making the definition. If f is a continuous function on the closed interval from a to b, here is what we are defining. The definite integral of f from a to b is the limit of left-hand or right-hand sums, it doesn't really matter, with n subdivisions of a to b as n gets arbitrarily large. So in other words, it's the thing that we were just working on. So it is denoted. How do we write it? It's sort of this elongated S, and we put the a and the b in this position. We write the f of x function here, and then we use a dx. And this is equal to that limit as n approaches infinity of the sum, I goes from 1 to n, of delta x times f of x sub I star. So that limit that we were working on in the last section, the last lesson. So what's basically happening here is we're defining this to be called the definite integral, and then this is how we're going to write it. So let me break down a couple more vocabulary words here. This elongated S is called the integral sign. Integral sign. Okay. The thing that you're taking the integral of, like taking the derivative of, or this thing that you're going to equation that you'll put here, is called the integrand. And it's a weird word, but you're going to want to use it because you're going to be doing so much integration in the next semester of your calculus life. And it's really annoying to say the thing you're taking the integral of. So the integrand is a very convenient word. A is the lower limit of integration. And shockingly, B is the upper limit. And together we just call them the limits of integration. Okay. So this is this new notation that just means the thing that we've already been working on. Okay. And be aware that the definite integral is a number, right? It's not like you're going to plug in a different x and get a different number. It's this whole limit. So it doesn't matter if you replaced the x, like you could write the integral from a to b of f of x dx, or maybe you decided you wanted to use t instead of x, f of t dt. So this dx, similar to how it was in derivatives, is really saying with respect to x, with respect to t. Okay, it doesn't matter if you change the variable you're using, as long as you have the same function. Okay, your graphing calculator does calculate definite integrals for you. Of course, in general, you're going to need to show the work to actually do it yourself, but you can check your answers. So usually it's under the math menu. I know every calculator is a little bit different, and some of the newer ones that actually will do it with the integral sign. So you're looking for the fn int command or button, I guess, program. And the way it works, depending if your calculator is a little older, it has you put in the lower limit, the upper limit, and then like the f of x equation, whatever it is that you're taking, whatever the integrand is, and then x, which means you're doing it with respect to x, right? And you literally do put these in with the commas. So for example, if you were trying to do the integral from 1 to 4, whoops, 1 to 4 of, let's say, x squared dx, then you would put in 1 comma 4 comma x squared comma x. So give it a try, play it around with a little bit, make sure that you can get your calculator to do that. Like I said, it's a great way to just check your work. Okay, so interpretations. What does the definite integral mean? Well, where did it come from? What were we doing when we first talked about this limit? Right? We were talking about an area under a curve, right? So when a function is strictly positive or non-negative on the interval. Okay. So for example, let's say my function did this, and the interval that I'm talking about has it, the function is completely non-negative. Okay, so it could be 0. Then what is that integral equal to? Okay. This is where this came from, right? It's the area under the curve, but above the x-axis. So this represents the area under the curve, f of x, and above the x-axis. And of course, it's cut off between a and b. So that is where we got this definite integral from. Okay. And actually, you can use that fact to calculate some integrals without doing a limit, right? Because especially when you see this, when it says interpret it as an area, that is a hint that you should be able to figure out what this area is by some sort of geometric formula. So the best approach when you see this by interpreting it as an area is to graph. Graph, what does this look like? So I'm trying to go from -1 to 1 of this curve. Do you recognize what this curve is? Some people will. And maybe you might need to do a little work to get there. So let's say we square both sides to get rid of the square root. Got it yet? Move the x over. Aha, it's a circle, right? It's a circle centered at 0, 0 with a radius of 1. And so you're going to get that a lot. If this was like a 4, it would have been centered at 0, 0 with a radius of 4. And it's actually not the whole thing, right? Because it's just the positive square root, then it's the top half. If it was the negative square root, it would have been the bottom half. So y equals the square root of r squared minus x squared. Oh, did I say if this was 4, then the radius would be 4? I meant 2, right? Because it's an r squared. Sorry about that. This is the top half of a circle radius r centered at the origin. And if there is a negative in front of it, then that would be the bottom half. I sort of squeezed my negative in there and didn't make it really obvious, which was sort of not what I was trying to do. Okay, so I'm saying that I'm looking at the top half of the circle. It's not my best work, but it will do, right? Of radius 1. And I am looking at the whole thing because it goes from -1 to 1. So how would I calculate that? Area would be 1/2 pi r squared, because I'm only doing half of the circle, which would be pi times 1 squared all over 2. So this integral, which is also represented by the area, is equal to pi over 2. Okay. All right, so moving on, what happens if the function is not completely non-negative? So when some of the values of the function are negative, and maybe some of them are also non-negative. So let's take a picture, or draw a picture, not take one, of something that could be, maybe we have a curve that's like this, and the A is here, and the B is here. So when I drop these vertical lines, I now have sort of, I'll call this A1. I have this region that's below, and I'll call this A2. And I have this region that's above the x-axis. So let's think about it a little bit. Remember that when we were doing the rectangles, I would take the delta x, which is always going to be positive, and then I would take the f of x sub I. So in this A1 region, when I do the f of x sub I, I'm going to get a negative number, right? So all of my heights will technically be negative, which will mean that when I calculate it using that sum, area 1 will be negative. Okay. So I'm just going to add that note here. F of x, x sub I star will be negative. In A1. So A1, when we calculate that up, will be a negative number. It will be the area, but it will be reported as a negative area. But we won't have that problem up here in A2. This is above, just like all of the ones we've done before. And so when we do the f of x sub I star, we're going to get positive numbers. So f of x sub I star is positive in A2. Okay. So A2 is positive. So what happens when I do the integral from A to B? I'm going to count this area as a negative and this area as a positive. So what that integral will represent, of course, I didn't leave myself a great spot, so I'll come over here, is what we call the net signed area. And it's basically where the area above is considered a positive, the area below the x-axis is considered negative. Okay. And so it's basically the area above the x-axis minus the area below. So that calculation will give me this minus this in terms of area. So just take a picture, or not a picture, I keep saying take a picture. Let's draw a picture that will kind of give us a distinct example of this. So let's talk about sine of x. Okay, that was maybe not the greatest set of axes. Oops. And we're going to go from pi over 2 to 2 pi. So I'll just draw the first period of sine, right? It's not my best, but not my worst work. Let's continue that out. And so we know that this goes to 2 pi. That leaves this with pi over 2, and of course 3 pi over 2. So if I'm looking at the integral from pi over 2, it's going to start here to 2 pi, so it will end here. So I'm looking at this region, again, I'll call it A1, and this region A2. Okay. And so basically this integral of pi over 2 to 2 pi will be A1 minus A2 if you're thinking of A2 as a positive area, right? It will be reported in the integral process as a negative area, right? And we would expect that answer to be negative because the A2 is a bigger area than A1. So kind of just giving you a picture to connect that to.